Error-aware policy learning, zero-shot generalization in partially observable environments. We present a novel algorithm that enables control policies for robots to transfer from a training to a target dynamical environment in a zero-shot manner. Our work focuses on transferring fault prevention control policies using assistive devices across multiple human agents. Humans display large variations across dynamical parameters. Some parameters are easily measurable, and some parameters are challenging to measure. We denote the measurable or the observable parameters as mu, and the unobservable parameters with the letter nu. Our goal is to learn a policy that overcomes the differences in dynamics caused by both these parameters and generalize to human agents with different physical characteristics. For example, here, a policy trained on a taller and a heavier person is transferred to a smaller person. Prior work on transferring control policies can be broadly classified into three different categories: domain randomization, system identification, and methods that adapt the policy in the target domain. Domain randomization methods often require manually engineered variations, and in tasks with large variations in the dynamical parameters, it generates a conservative policy producing suboptimal actions. Accurately identifying human behavior can also be a challenging task due to many unobservable parameters and lack of sufficient human data. Methods that improve the policy in the target domain requires deploying the policies. Now, deploying policies that apply forces on human subjects can be potentially dangerous without prior testing. Our algorithm tries to address these shortcomings. We define a dataset which comprises of human agents with different physical characteristics. We then split the dataset by randomly choosing one of the environments as a reference environment and label the rest as validation environments. Our algorithm uses a quantity called state error. It is defined as follows. When an action A is applied to a robot at state S, state error is the difference between the two states resulting from following two different transition models. Let's assume there exists an oracle error function that takes in as input the state S, the observable parameter, and action A, and outputs a state error between the validation and reference environments. Our hypothesis is that the policy which is aware of the state error can take better actions. However, such an oracle error function does not exist. Our algorithm aims to learn the error function and the policy simultaneously in a two-step process. Here, we describe the process of training an error function. First, we train a policy in the reference environment with the error equal to 0. Then, we apply this policy to validation environments. In the process, we collect the observed state errors in each environment. We then train an error function using supervised learning. To train an error-aware policy, in the validation environment, we first query an action assuming the error equal to 0. We then query the error function to predict the expected state error, and using which we finally compute a corrected action which is deployed to the robot in the validation environment. The policy is then updated using a reinforcement learning step. These two steps, learning the error function and the policy, are iteratively repeated until convergence. In the test environment, we simply use the observable parameters of the test robot. We compare our approach to two different baselines, domain randomization and universal policy. We test our approach on 5 different human subjects. We see that our error-aware policy beats the baselines, universal policy, and domain randomization in most of the tasks. We also use stability region as a metric to compare the performance of the policies. We see that the area of the error-aware policy is more than UP and DR. This plot represents the maximum force in each direction that the policy is capable of recovering from. So larger the area, better the performance. We also test our algorithm on different tasks: quadrupedal walking, hopper, and walker 2D. We see that our error-aware policy beats the baselines in all the tasks. Thank you.